Hey guys, in this video we're going to be covering the second half of section 5.4, so 5.4.2 if you will, which has to do with complex numbers. Now in the first half of this section, we talked about imaginary numbers, I, what makes a number imaginary, those square roots of negative numbers. Today we're going to be focusing on complex numbers, which we didn't use this term in the last video, but complex numbers are numbers that have two parts to them, a real part and an imaginary part. And so the general kind of way we talk about complex numbers is anything that has an a plus bi, an a part, which is the real part, and then the imaginary part, which is how many i's there are, bi. So for example here, 3 is a real number. We've been working with that forever. 3 is a real number. 8i is an imaginary number. We talked about those a lot on in the last video. And then 3 plus 8i, that is one number that has both a real and an imaginary part, which makes it, one with the highlighter, which makes it complex. So when we use the term complex number, it means it has a real part and an imaginary part. Okay, so that's kind of the first thing to know. And today what we're talking about in this video are the operations we can do. How do we add complex numbers together? How do we subtract them, multiply them, divide them? How do we tell if they're equal? What makes two complex numbers equal? So those are all the things we're going to be covering in this video, second half of 5.4. So to start, what makes two complex numbers equal? So if we make the statement, or if we are told that a plus bi is equal to c plus di, so if one complex number equals another complex number, that means two things. First, the real parts have to be exactly the same. We have to have the same number of real parts. So a and c have to be exactly the same. And second, the imaginary parts have to also be the same. We have to have the same number of i's in both of those numbers. So what does this mean? Basically, they just have to look exactly the same. 5 plus 4i equals 5 plus 4i. 8 minus 2i equals 8 minus 2i. So you're going to see some problems. I'll leave it zoomed out a little. Let's say solve for b and n. If we know that 3 plus bi equals n plus 7i. Well, if they're equal, we know the real parts must be the same. So that means that, well, n must equal 3 so that they match on the left and right hand sides of those equations. We also know that the imaginary parts must be the same. bi has to equal 7i, which means b has to equal 7. And so kind of our final answer here, we could just say that b comma n equals 7 comma 3. Those are the two values for b and n that would make these two complex numbers equal to one another. So real parts have to match and imaginary parts have to match. Let's make it a little more complicated, not too much, but that's the basic premise. 3 minus 2i is equal to x plus quantity y minus 2i. So again, kind of starting off, we know the real parts have to match. So that means x equals 3. We know the imaginary parts have to match, and so we might have to do just a tiny bit of legwork. On the left, we have negative 2i's. On the right, we have y minus 2i's. So what does that mean? We can kind of divide that I out on both sides. So negative 2 equals y minus 2. Add 2 to both sides. It looks like y equals 0 here. So we set it up and we say, what x value, what y value would make this equal? That means we need the same number of real, same number of imaginary on both sides. So x comma y equals 3 comma 0. And that'll make these two complex numbers equal. Okay. One more kind of like this. 2 plus x plus 3 minus ni quantity is equal to 8i. So using the same colors, let's make sure our real parts match. 2 plus x has to equal, what is the real part on the right-hand side? Well, it doesn't show up, so it's a 0, right? It's that invisible 0. So 2 plus x has to equal 0. That just means x equals -2. Right here, we know that 3 minus n has to equal 8, so that the imaginary parts match. 3 minus n equals 8. So that means that -n equals 5 if we subtract the 3. N equals -5 if we divide by that -1. So n comma x, I just like to put them in alphabetical order. -5 comma -2. So this is how we tell and can find complex numbers that are equal. The real part has to match, the imaginary part has to match. Okay. What about addition and subtraction? Complex addition and subtraction, not a big deal at all. You can think of it just as combining like terms. We're just going to combine the real parts and combine the imaginary parts. So you see here, the first problem on the screen, 5 plus 7i plus 11 minus 4i. We're just going to come here and combine the real parts. So 5 plus 11 is 16. 7i's plus -4i's, so 7 minus 4 plus 3i. 16 plus 3i. We just combine those like terms, those real parts together, those imaginary parts together. You can guess it's exactly the same with subtraction. You just got to watch out, make sure you are subtracting. So 3 minus 6 would leave us with -3. And -i minus 4i's would be minus 5i. So again, just combining like terms, combine those reals, combine those imaginaries, and then make sure you watch out for if it is a minus, that's a really common mistake, not actually subtracting and doing like 3 plus 6 or -i plus 4i, something like that. Make sure you are following the operation stated. All right, what about complex multiplication? Two numbers here, two complex numbers that are being multiplied by one another. 6 plus I times 11 minus 4i. So it looks like two binomials, and so we're just going to FOIL this as we usually do. It just has one extra step at the very end, but we'll get to that. So 6 times 11 is 66, minus 24i's plus 11i's minus 4i squared. And so if this were just real numbers, real binomials being multiplied, we would then typically say, okay, so that's 66, let's combine those like terms, minus 13i's minus 4i squared. But here's what we're going to do instead. If you remember from the first half of the section, we always want to simplify anything that is a larger power than I to the first. What is I squared? Well, if you remember, I squared equals -1. We made that table, we made that chart. So really, right here, when we have minus 4i squared, we have minus 4 times -1. And so we have 66 minus 13i, and then kind of a plus 4, that minus, and then you multiply -4 minus the -4. So 70 minus 13i is where this one ends up. And again, it all comes from I squared, which we got when we FOILed, being the same as -1. So we always want to replace our I squareds with a -1. That meant that highlighting green, this guy here ended up being a plus 4. So that's where we got the 70. So make sure you are simplifying your I squareds. Make sure when you're multiplying, whenever you get an I squared, it ends up as -1, and then you simplify further. So we just kind of powered through a bunch. We powered through equality, we powered through addition, subtraction, multiplication. Division is where we slow down a tiny bit. It's not too much. It's not too bad, but it's a little bit harder than just combining like terms. So if you remember, when we've studied radicals in the past, square roots, we said we don't ever want to end up with the square root on bottom. And so similarly, if we're dividing, we do not want a complex number in the denominator. If we have i's in the denominator, that's no good. And so we're going to simplify that fraction, that complex fraction, using something called the complex conjugate. Now, you might have heard this word before. Conjugate takes on a few different roles in math. But here's what it is. The complex conjugate of a plus bi is a minus bi. They are a pair. They are linked in mathematics. A plus bi, a minus bi. So whatever the sign of the imaginary part is, you can find the conjugate by just flipping that sign. If it was a minus, turn it to a plus. If it was a plus, turn it to a minus. So right here, just to make sure we understand the concept, what is the complex conjugate of 4 plus 6i? Well, that would be 4 minus 6i. 8 plus 3i, 8 minus 3i. And here's the one that I tried to trick you on. 19i minus 14. Remember, to get the conjugate, we need to switch the sign of the imaginary part, which means I'm going to change colors just to make sure everyone sees this. Negative 19i, we change that sign and leave the real part alone, minus 14. Always changing the imaginary sign, leaving the real part alone. So in this last one, 48 plus 5i would be the complex conjugate. Hopefully that makes sense. Pause or rewind it if you need, but we're always just changing the sign of the imaginary part. So awesome, we can find the complex conjugate. How does that help us? Because to divide complex numbers, we write them as a fraction if they're not already written that way. And we're going to multiply the top and bottom by the complex conjugate of the denominator. And then we're going to simplify. And you're going to see what this does, how this solves the issue of having complex numbers on the bottom. So first problem here, we have 4 plus 3i over 2 minus I. We do have a complex number on bottom because it has that imaginary part. So here's what we're going to do. I'm going to zoom in a little bit. 4 plus 3i over 2 minus I. And in step 2, it says multiply top and bottom by the complex conjugate of the denominator. So what's my complex conjugate of the denominator? It would be 2 plus I, right? Flip the sign of that imaginary part. So 2 plus I, 2 plus I. We multiply top and bottom by the same thing to keep the fraction the same. And then here's what I like to do. Especially when we're starting out, I want to just simplify the bottom, just simplify the denominator. So let's FOIL it out. This is more like multiplying practice. 2 times 2 is 4 plus 2i minus 2i's minus I squared. So we will have to FOIL and simplify the top. I don't want you to think we don't, but I want to keep going on this denominator here just for a second. Plus 2i minus 2i. Those are gone. And I'm hoping you can see and maybe pause the video and reason out why that will always happen when we multiply by the complex conjugate. We'll get plus 2i minus 2i or plus 7i minus 7i, and they'll always cancel out. So what does that mean we're left with, though? That means we're left with 4 minus I squared on bottom. But if you remember from our multiplication example, we said we don't ever want an I squared because I squared is just negative 1. So what is this really? This is 4 minus a negative 1. And it looks like we get 5 on bottom. And this is what will happen whenever you multiply by the complex conjugate of the denominator, is the i's are going to disappear. We're going to be left with an I squared and a number but we know what I squared is. It's -1. We always simplify it. In this case, it came out to be 5. So continuing on, let's just make sure. So we get 8, we'll FOIL the top, plus 4i, plus 6i's, plus 3i squared. We see an I squared. We know we'll probably be getting rid of that here soon. So 8 plus 10i's plus 3i squareds. We know that that is -1. So 3 times -1 there is -3. So we get 8 plus 10i minus 3, basically, plus that -3. 5 plus 10i. So 5 plus 10i on top. You're looking at this fraction, I'm hoping, and saying, I think we can simplify that. It's pretty typical, and here's how I advise doing this. To write your final answer as a complex number. What I mean by that is a real part and an imaginary part. So I'm going to break this up. I'm going to say, so 5 over 5 plus 10 over 5i's, and that's kind of the a plus bi form. So the last step, let's just simplify those fractions. 5 over 5 is 1 plus 2i. Will it always work out perfectly where they simplify the whole numbers, integers? No. But this is how we divide complex numbers. I know it looked like a lot of steps, but what did we do? We multiplied by the complex conjugate of the bottom, 2 plus I. We started FOILing and simplifying, so the 2i's went away. We combined like terms. We see that I squareds become -1s. We simplify a little further, and then we write it as our complex number. Okay, this is definitely the most involved of all of the operations on complex numbers. So we're going to do a couple more examples, then call it a day. So next one, 3i over 2 plus 4i. Let me grab my charging cable real quick. It fell to the floor. All right, 3i equals 2 plus 4i. We're definitely dividing that by a complex number here. So what do we want to do? 3i over 2 plus 4i, and we want to multiply by, keep the colors consistent, red. We want to multiply by the complex conjugate of the denominator, and we want to do that on top and bottom. So 2 minus 4i. 2 minus 4i. So let's start distributing and FOIling. So again, I like to do the bottom first, just to make sure that I multiplied by the right thing and I end up without any i's on bottom. So 4 minus 8i plus 8i minus 16i squared. And we can see on bottom, minus 8i plus 8i is gone. We get 4 minus 16 times -1. Because that's just a -1. So 4 minus -16 is kind of 4 plus 16. That's just going to give us 20. So I'll pause there. I feel good about my denominator. I got rid of the i's. They're not complex. Up top, we're not FOIling, but we are kind of distributing. So 6i minus 12i squared looks like. But we know that this I squared is a -1. So we say 6i minus 12 times -1. So that means we have 6i plus 12. And I'm going to rewrite those in the form we usually see, which is the real part first, then the imaginary part. So I'm just going to say 12 plus 6i over 20, a plus bi. And then let's break it up, break this fraction up into those real and imaginary parts. So 12 over 20 plus 6 over 20 i's. Just put the I out front. And finally simplify those fractions. Maybe divide the 12 and the 20 by 4. So 3/5 plus divide the 6 and the 20 by 2. 3/10. I. So again, here's a good example where it didn't come out to be perfect, beautiful integers, but it is a complex number. It's still 3/5 plus 3/10 I. Nothing wrong with that. So I'm hoping that this process of dividing complex numbers makes sense, and I'm hoping it actually, you're looking at this and saying, okay, I get it. It's really just multiplying by the conjugate and simplifying. What I'd love for you to do is try this one on your own. Pause the video. I'm going to pause my screen. I'm going to work it out, and then I'm going to unpause, and you can compare your work to mine. But pause the video right now and try to work out 2 plus I over 1 minus I, multiplied by that complex conjugate on top and bottom, and then simplify both top and bottom until we get a nice complex number at the end. All right, so hopefully you had a chance there to work this problem out. Multiplied by 1 plus I on top and bottom, that complex conjugate, simplified, FOIL, distributed, change those I-squareds to -1s, and you can see my work here. You can pause it if you need to check my work against yours, but I do end up with 1 plus 3I over 2, and splitting that up into real and imaginary parts, 1 over 2 plus 3 over 2I. So guys, this is complex numbers and all the things we can do with them: add them, subtract them, multiply them, divide them, set them equal to one another. And so this is the second half of section 5.4. Now, some of your practice problems are going to give you practice in this, and we want to get it just to muscle memory. I's are new, complex numbers are new. They're kind of on this whole new plane of existence. But once we learn these basics, we'll be able to do a lot of things with them. We'll be able to solve more quadratic equations, as we've seen. So hopefully this makes sense. If you had questions, if you weren't sure of something, please let me know. Maybe write it down so we can talk about it next time that we all meet in person. But until then, enjoy, and yeah, welcome to the world of complex numbers.